In today's lesson, we're going to look at a variety of different alkyne reactions. And the simplest way to think about alkynes is to try to do the same chemistry to the alkyne that we would have done to an alkene. And so we'll think about the alkene reactions first and then decide if we can do the same chemistry to the alkyne. In this reaction right here, there is an alkene, and we can react it with the molecular halogen, either bromine or chlorine, as Br2 and Cl2. They will undergo electrophilic addition, characterized by this arrow that hinges away from the pi bond, but it skips the carbocation intermediate, forming the halonium ion instead. And in the second step, another halide ion, the one that got bounced off in the first step, will come along and pop this open via backside attack, and we end up with our vicinal dihalide. When we look at the alkyne and whether or not it can do the same chemistry, the short answer is yes, exactly the same chemistry. Mechanistically, these are identical. The only feature that is kind of worth noting is first, well, there's two features. The first is that because our product of alkyne halogenation still has a double bond in here, that limits its ability to rotate. And so the two halogens will end up anti relative to each other, and they're locked in that arrangement by the pi bond. So this adds two halogens to your alkyne, but it adds them in an anti orientation. You'll notice, though, that the alkene that we produce at the end of this reaction is similar to the alkene that we started with in the top reaction. And so if you continue to let this reaction cook in the laboratory with an excess of molecular halogen, it will go through these two steps and you'll end up producing a tetrahalide. These two arrows right here are a luxury that is afforded to somebody who has already passed organic chemistry. You are not allowed to do this, but it just denotes that there's some stuff that happened here and ultimately we get this. Your job as a student is to be careful in stating what that stuff is, and that stuff is this mechanism right here. So it goes from an alkyne to an alkene via these two mechanistic steps, and then there are two more mechanistic steps to take your anti-dihalide into a tetrahalide. These vicinal dihalides that we produced from an alkene in the previous mechanism are a useful starting material for generating an alkyne via dehydrohalogenation. It's actually referred to as double dehydrohalogenation because every time I pop off one of these halogens, along with its associated anti-beta hydrogen, I end up with a pi bond, and if I do that twice, then I can end up with a triple bond. So that's the reaction we're going to look at next. How do you make an alkyne from this vicinal dihalide? The beta elimination that we get in this reaction is interesting because there are actually two different alpha positions to consider. An alpha carbon is a carbon that is directly connected to the halogen leaving group. So that means that this carbon right here is one of my alpha carbons, and therefore these two carbons to the left and to the right are both beta carbons relative to this alpha carbon right here. This carbon over here is also an alpha carbon if we consider the world from the perspective of this halogen, and therefore this carbon is also a beta carbon. So when I think about elimination, I have to think about every single carbon as a potential source of beta hydrogens. That's why I've color-coded these here. The black hydrogens right here, the blue hydrogen, and then the red and magenta hydrogens. The black hydrogens, according to Zaitsev's rules, are the least important. Remember, with Zaitsev, when we use a base, we pull the hydrogen from the carbon with the fewest number of hydrogens. So when we do an elimination to produce an alkyne on this vicinal dihalide, these hydrogens out here don't participate in that chemistry. So I'm going to leave them out and just focus on the remaining three hydrogens right here. Now, according to Zaitsev's rule, when you have two different potential beta carbons, right, so this carbon right here is beta relative to that leaving group, and the carbon on the right-hand side is beta relative to this leaving group. We pull the hydrogen from the carbon with the fewest number of hydrogens, so the blue hydrogen is the first one to go. And with one elimination step, we can end up with a vinyl halide, and we're halfway there. This is the base that we use for this reaction. The amide base is both a strong base and a strong nucleophile, kind of like ethoxide and methoxide. The difference, though, is it's so much better as a base that it doesn't do a lot of substitution chemistry. So you can use amide even though it's a small, strong base, and it ignores the nucleophilic attack because it's such a strong base. So we end up producing this vinyl halide right here. In the presence of amide, this reaction just keeps going. And in fact, it gets a little faster with each step that I show you. So pulling a hydrogen off of an sp3 carbon is harder than pulling the hydrogen off the sp2 carbon, so it kind of rolls downhill. The first step is the slow step, and then the second elimination. So this is E2 and then E2 back to back. And the second E2 is going to go faster because of the change of hybridization of that carbon. We end up with this alkyne, which is what we wanted. The problem is the amide base is strong enough that you can't really stop it, and it will continue to rip that hydrogen off. And so instead of getting the alkyne that you want, you end up going a step further to produce what's called the alkynide ion. Normally, the amide comes in a box with sodium ions, and we use ammonia as a solvent simply because the easiest solvent to use with any strong base is its own conjugate acid. So the conjugate acid of amide is ammonia, and you can evaporate off ammonia fairly easily, and this compound precipitates out as a sodium alkynide ion. And so we precipitate this, you can wash it with a little bit of ammonia, clean it up, and then you transfer this to the next reaction container when you're doing the chemistry. This is not usually the compound that you want. We simply we start off with a vicinal dihalide, and we can make this compound right here. There is an alternate way of running this reaction, and what they use instead is potassium terbutoxide. The terbutoxide is the active ingredient in potassium terbutoxide, and it is capable of stopping once you get to the alkyne. It undergoes two sequential E2 elimination reactions. Remember that this is a large bulky base, so it attacks the anti-site F hydrogen, the one where there's more hydrogens instead. So that's why I pulled the magenta off here first. It just doesn't fit nicely into the middle. But once you get to this position, the whole molecule flattens out, and so the terbutoxide does not have a steric problem then pulling off the blue hydrogen. We get to this stop, and terbutoxide just can't do this last step right here. It's not a strong enough base to pull those hydrogens off. And so you can get this reaction to stop at the alkyne if you want by using potassium terbutoxide. Most of the time, the chemist will just use sodium amide, run it all the way through to this ion right here, and then you just add water, just pipette distilled water in the laboratory. It's an easy, cheap source of water. So the alkynide ion will come along, pick the hydrogen off of water, and you end up making your alkyne. And so while on paper it seems tedious to go past the product that you want and have to add in water in an additional step to get back to that product, in the laboratory, this top pathway here is kind of the easiest way to go. So this is from start to finish what we did across the top right here. We took an alkene, we added a molecular halogen to it to get to this vicinal dihalide. Then we used sodium amide to take it to the alkynide ion, and then we used water to put the hydrogen back on the end. If instead we had just used potassium terbutoxide, then we could have done it in fewer steps. And on paper, you'd want to go with the fewer steps. That's usually the easiest route. But in the laboratory, it's a lot easier to use sodium amide and water, and largely because the conjugate, potassium terbutoxide is a strong base, so you want to use its conjugate acid as a solvent. The conjugate acid of potassium terbutoxide is terbutanol, which has a melting point of about 27 degrees Celsius, which is slightly higher than room temperature. So when you have a bottle of terbutanol that you're using to solvate the potassium terbutoxide, the first thing you have to do is melt your solvent and warm it up to 27 degrees Celsius, which is kind of a pain in the laboratory to wait for something to melt to start your day's worth of chemistry. So most chemists would prefer to go this route. Just if you do want to get to the sodium alkynide ion, then all you have to do is add in the molecular dihalide and the sodium amide. You don't necessarily have to add the water unless you want to put the hydrogen back on again. So this is yet another option of things chemists could do in the laboratory. And you only need to add the water back in if the alkyne that you end up producing right here is a terminal alkyne. In other words, if instead of having excess hydrogens out here on this alkene, I just had an extra methyl group right here, then this reagent right here would produce this product, but this hydrogen would instead be a methyl group. And the amide's not going to rip a methyl group off, so it will just stop once it gets to the alkyne. So this water addition step and the potential use of potassium butoxide is really only a consideration that you have to deal with when you're working with a terminal alkyne. If it's the alkyne embedded in the middle of the compound, a disubstituted alkyne, then you don't have to worry about that. And finally, in this idea of starting with an alkene first is just kind of a review of the mechanisms that we learned in the previous chapter. So you can just start directly with the vicinal dihalide occasionally. It's not like this reaction needs a running start. You don't have to start with the alkene and then make the dihalide and then carry it through to the alkyne. You can just start directly with the dihalide. And then this is a terminal one, so we have to use the water step at the end. In addition to synthesizing alkynes for their own sake, one of the more useful reactions that we get out of this section on alkynes is a nucleophilic carbon. So most of the time we've seen carbons that are carbocations. This is a case where we have a carbanion. And a carbanion is a nucleophile, and we can use this carbanion to plug into an alkyl halide and make a carbon-carbon bond. And that is a very big deal to a chemist. In fact, this is, besides free radical polymerization, this is the first time that we've shown you how to make carbon-carbon bonds. And this is a big deal. It's how we approach deity as chemists, by making things with carbon-carbon bonds. So the problem with this reaction is that it is an SN2 reaction. SN2 reactions are always in competition with E2 reactions. And so if you want this reaction to be a substitution reaction and to produce the carbon-carbon bond right here and not be an elimination reaction, then this R group right here is limited to methyl and primary groups. Let me give you two examples that illustrate that. So this right here is ethyl halide. I didn't specify the halogen, so it's some halide. So there's an ethyl group connected to a halogen. This is a primary alkyl halide. When I react this with my alkynide ion, and this R group over here can be, here I just have a propanide ion, but you can have other R groups back here, doesn't really matter. This is the business end of the molecule, and the carbon with a negative charge will plug into this electrophilic carbon, and we just ended up making a carbon-carbon bond. And that, again, is a big deal. It's not often that we know how to make carbon-carbon bonds, and they're difficult to make. Anytime you have an SN2 reaction, that means you're also going to have the E2 competition. So in red arrows here, I have shown you the elimination reaction, where instead of making it all the way into the electrophilic carbon, your nucleophile gets sidetracked, picks off one of these hydrogens instead, and we end up forming the elimination product. And if you really want the elimination product, then just buy a box of sodium methoxide. It was a waste of everybody's time for you to turn this alkyne into an alkynide ion if all you want is that thing to act as a base. This is a very difficult to make base. And so this is typically, the red arrows here do not typically represent chemistry that you want to occur. The whole purpose of making the alkynide ion is to use it as a nucleophile and not as a base. If you want it as a base, then you're an idiot. There are better bases to use. So the SN2 reaction here is my major product because this is a primary alkyl halide. If instead I react to this same alkynide ion with a secondary alkyl halide, so this is some 2-halopropane, then on its way into the electrophilic carbon, this carbanion right here, instead of doing a substitution reaction, is much more likely to get sidetracked by one of these 6 beta hydrogens, and the red arrows kind of bounce down and we end up making an elimination product. Because this is both a strong nucleophile and a strong small base, from the alkyl halide table from the previous section, a secondary alkyl halide reacted with a strong nucleophile, strong small base, we expect E2 to be the major product. And this is not a good use of an alkynide ion. Again, these are very difficult to make compared to buying sodium methoxide and just using that to do E2 chemistry. So that's why when you run this reaction right here and you want to produce that carbon-carbon bond, you got to make sure that your target molecule is an alkyl halide where the R group on that alkyl halide is a methyl or primary group. This reaction right here is a review of catalytic hydrogenation. In catalytic hydrogenation, we talked about in the alkene chapter that that an alkene in the presence of a catalytic metal will add molecular hydrogen to go from an alkene to an alkane. In alkyne chemistry, which is the focus of this chapter, we see the exact same catalytic cycle with all the same features, and it ends up producing turning your alkyne into an alkene. So remember, the first step is the oxidative addition, where we're adding molecular hydrogen to our metal and we're oxidizing the metal to a 2+ state. We still use the same metal catalyst that we used in alkene catalytic hydrogenation, such as palladium, platinum, nickel, and RH, which I always forget the name of. In the second step, so this was the oxidative addition, and then we have the coordination step, where the metal now with a 2+ charge will attract the pi system of the alkyne. In this particular step, where the alkyne's pi system just leans into the positively charged metal, is going to show up again towards the end of today's lesson. Different metal is going to do it in a later step on a different mechanistic pathway. But this is hopefully something that we saw before, that you've seen before. So again, oxidative addition, coordination. Now that everybody is kind of loaded up on the metal surface, then one of those hydrogens slides into the alkyne. This is the insertion step, and then the second hydrogen leaves the metal, slides into the what's now an alkene, and we end up with our reductive elimination step. One thing that's important to note is that the two hydrogens that I add to the same side of the original alkyne. This is referred to as syn addition, and this is important. If you think about this from a chemist perspective, we just turned our alkyne into an alkene, and the two new hydrogens that we add are cis relative to each other. Under normal catalytic hydrogenation, this alkene that we just produced will immediately run this lap again. So because of syn addition associated with catalytic hydrogenation, this alkene will be cis at the end of the catalytic hydrogenation. This alkene now reacts, so the metal will continue to react with hydrogen, oxidative addition, but now we have alkene present inside of our reaction container, so that coordinates with the metal, and then we end up with the full reduction of the alkyne that we started with. First becomes an alkene, and then the alkene is reduced all the way down to the presence of an alkane. And now the alkane carbon-carbon bond is free to rotate, and you wouldn't notice that syn addition that we saw at the end of the first step simply because it could undergo rotation. Now, the triple bond in an alkyne, that second pi bond, is much, much more reactive than the pi bond of an alkene. And so that means that this loop right here is happening many orders of magnitude faster than this loop right here. And if you were extremely fast in the laboratory under normal catalytic hydrogenation, the alkyne would undergo catalytic hydrogenation in a matter of maybe milliseconds, a thousandth of a second or even faster. And then this alkene would undergo the reaction, over the time frame of seconds. So this is 1,000 times faster than this. I don't know for sure what the numbers are, but just follow with me. This is 1,000 times faster. But from a human perspective, both of these reactions are occurring so fast that you would not be able to reach into the reaction flask and pull out that alkene. And so what we need to do, because chemists want that alkene, this is a cis alkene, and that's kind of a big deal. And so if you want that cis alkene and you want to pull that out of the system, then what happens is you need to slow this down. So you don't want to remove the catalyst entirely because then it's too slow, but you want a catalyst that just kind of works a little bit. So the alkyne reacts much faster than the alkene, Therefore, if you slow all of the chemistry down, you should be able to get the alkyne to react in a matter of seconds and the alkene to react in a matter of maybe tens of minutes. So then you let the reaction run for a handful of minutes. It's definitely enough time for all the alkyne to become alkene, but your alkene is still kind of taking its time working its way through the system. And so a fellow by the name of Lindlar came up with this, and what he discovered was that if you take a regular alkyne and you push it through catalytic hydrogenation, you'll take it all the way to an alkane, which is not what he wanted. He wanted the alkene. So what he did is he started mixing things with his palladium, and this was the kind of the sequence of stuff that he put into the palladium, and it slowed the catalyst down. They called it a poisoned catalyst. So it still caused the reaction to go faster than not having a catalyst at all, but it did cause it to go slow enough that he could turn off the stream of hydrogen gas, get the reaction to stop at the alkene, and ended up getting the cis alkene out of that. These are a lot of reagents for you to remember, and so I just refer to it as hydrogen in the presence of Lindlar's palladium. If you do see all of the reagents associated with Lindlar's palladium, there's really nothing else that we add to palladium to do any organic chemistry in this class besides Lindlar's palladium. So if it's palladium plus anything extra, specifically identify maybe one of these three compounds, then it's going to be Lindlar's palladium. But it's common for people just refer to this as Lindlar's palladium. The point of Lindlar's palladium is to be able to do a stereochemically controlled catalytic hydrogenation of an alkyne to produce the cis alkene. Before we move on, let's stop for a minute and think about what it is that we've seen so far with alkyne chemistry. Here is the starting material alkyne. In the previous lesson, we looked at adding sodium metal and ammonia in a free radical reaction to convert that alkyne into a transalkene. We just finished looking at how we can use Lindlar's palladium to convert the alkyne to a cis alkene. And before that, we looked at adding molecular halogens to the alkyne to produce first the dihaloalkene, where the halogens are anti or trans relative to each other. And then if you continue running that reaction, you can produce the tetrahaloalkane. Here in asterisks, I have indicated whether the mechanism is identical to what we saw with alkenes or similar. So far, we haven't seen any mechanisms that I would characterize as similar because what we've looked at so far has been identical. These steps were mechanistically identical to what we saw with alkenes, and this step was mechanistically unique. We saw nothing like this with alkenes at all, so that's why there's neither one nor two asterisks? I have no idea. 2 stars. I should edit that. All right. Now we're ready to start thinking about a reaction that is not identical to what we saw with alkenes. And there's a reason that you'll be able to predict when an alkene reaction will work for an alkyne and when it won't. So here is the addition of halogenic acid to an alkene. This is electrophilic addition. The pi system hinges out to go pick up the hydrogen. We form a carbocation, and then the halide ion captures that carbocation. And we've added a hydrogen and a halogen to our alkene. So this is a mechanism from the previous section. Whenever you look at what the alkene does, you can try to do the same chemistry with the alkyne just by putting a triple bond in there. So now I have the alkyne. And just to kind of help you see the similarities of these reactions, I went ahead and left my alkyne bent, even though it should be 180 degrees. So ignore the geometry here. The pi system for the alkyne would reach out to pick up the hydrogen. We would end up forming a carbocation intermediate, and then the halide ion would come in here and attack that carbocation, and we could potentially end up with the same product. This is not going to occur like this. This mechanism on the bottom is wrong. And the key problem is this carbocation right here. This particular carbocation is referred to as a vinylic carbocation. It's a carbocation that occurs directly on a carbon that is participating in a double bond. And these are highly unstable. Kind of ballpark, in the same ballpark as a primary carbocation. So we don't expect for this mechanistic pathway to work. And instead, what we do is we end up essentially combining both steps rather than the pi system reaching out to grab a hydrogen and then the halide ion attacking the carbocation. We just kind of crunch them together. So this is still electrophilic addition, but both of these things happen at the same time. The pi system reaches out to grab the hydrogen at the same time that the halide ion comes in and attacks that carbon. Because this happens at the same time, that means that the halogen that we just add and the hydrogen that we add end up adding anti relative to each other. Now, a good question you might ask is, where does the very first halide ion come from? Because you can imagine that after the first chemical reaction has run, you're definitely going to produce a halide ion, but where did the first one come from? And the answer is it's simply the nature of a strong acid. Halogenic acids tend to be strong acids, which means that in any solution, even an organic solvent, there's an equilibrium that's going to produce some free halide ion. And so occasionally I've seen mechanisms where they will go ahead and show this as an HX. They will show the hydrogen being plucked off at the same time that the halide ion comes in to stick to that carbon. That's not entirely incorrect, but I prefer this mechanistic view here a little better. This is an inorganic step, so you can just assume that this happens. You'll also notice for the first time a third order reaction overall. This is concerted, meaning everything happens in a single step, so this must be the rate determining step. And if this is the rate determining step, then that means there are 1, 2, 3 different species involved in that rate determining step. The rate of this reaction experimentally is equal to some experimentally derived rate constant times the concentration of your halogenic acid squared, meaning that 2 of them are involved in this rate determining step times the concentration of the alkyne. There is some debate as to whether or not this third order reaction is even is probable. And your current version of the textbook actually doesn't show a mechanism, I don't believe, because it just kind of gives up on the debate. But I think the consensus among the scientific community is that this third order mechanism is probably the best way to show this reaction. You can control this reaction stoichiometrically, meaning that if you add in a limited amount of halogenic acid, the reaction will stop when you get to this point right here. And the reason for that is the alkyne is more reactive than this resulting alkene. But if you flood the system with halogenic acid, then you expect the alkene to continue to react with another equivalent of halogenic acid to produce the carbocation in a mechanism that is identical to what we saw alkenes do originally. So it's okay to have this carbocation because this carbocation is not part of a carbon that's making a pi bond. It's not vinylic. And so the question, though, that you should ask is, why does the carbocation show up directly underneath the halogen? And the argument that should be made is, isn't it destabilizing to put a positive carbon directly adjacent to an atom that is pulling electron density even more off of that carbon? And the short answer is, that's a good question. The long answer is that resonance actually allows for this to occur. So in addition to this carbocation right here, there is a resonance structure where one of the lone pairs from this halogen will hop down to form a carbon-halogen double bond. That's this blue arrow right here. And if you can show an arrow pushing mechanism to make one of your resonance structures, it is equally correct to show an arrow pushing mechanism to get to the other resonance structure. The existence of the resonance delocalization of the positive charge from the carbocation to the halide to the halogen stabilizes the carbocation better at this carbon as opposed to this primary carbon over here. So in the second step, when the halide ion comes and attacks the carbocation, we end up with both of these halogens attached to the same carbon. This is referred to as a geminal dihalide in contrast to a vicinal dihalide. Vicinal is where the two halogens are on adjacent positions, but when you add halogenic acid in excess to an alkyne, ultimately you should end up with a geminal dihalide. In the previous section on alkenes, we learned that if you add an alkene to hydrobromic acid, HBr, But you do that in the presence of peroxy radicals or UV light or heat. Right? So we typically use peroxide radical generators, which are OR groups and OR groups. Then the alkene ends up adding the bromine to the anti-Markovnikov position. So your bromine ends up out here on the end of the compound, and it places the hydrogen at that Markovnikov position. Okay? So this was the reaction that we saw for alkenes, and this was the standard free radical chemistry reaction that has an initiation, a carbon radical formation, and then a propagation step. So let's take a look at those. Okay? So this is the initiation step where there's kind of a pre-initiation step where your peroxy radical makes the actual radical. That then plucks apart via 3 half-headed arrows, your HBr, to produce the bromine radical. This particular reaction, the anti-Markovnikov addition of bromine to a pi system, works for bromine and not chlorine. It's one of those times where we have to be very particular about which halogen we're using. Now that we've initiated the reaction inorganically by getting this bromine ready, and again, this is the bromide specific, and chlorine doesn't work, then the bromine is involved in the carbon radical formation, 3 half-headed arrows. And the reason that the bromine ends up at the less substituted or anti-Markovnikov position is so that the free radical can be at the more substituted or Markovnikov position. And then in our final step, the propagation step, it's where that radical carbon will now pluck apart a molecule of hydrobromic acid to produce the final organic product and reproduce the bromine radical that started the whole system. That's why it's called propagation. You end up making your product, but you also reproduce the original radical that started the chemistry. All right, this was a review of alkene chemistry. Let's see what alkyne chemistry offers us. If I just take this double bond and turn it into a triple bond and try to do the exact same chemistry, then the sticky point here is this vinylic radical. Now remember, if you make a vinyl cation, then that mechanism will not work. Okay? For all of the examples that we'll show you in this course with this textbook. And we have to come up with a different mechanism. But if you have a vinylic radical, those are problematic but not prohibited. So mechanistically, this goes exactly the same route. So everything that you learned about alkenes, we just kind of reproduce, copy and paste in terms of your understanding of what alkynes are going to do, and we end up with an anti-Markovnikov vinyl bromide. Now, if you continue to add HBr under free radical conditions to this reaction, I'm not entirely sure what happens. And so usually when I get to this point, I just stop. I'm not sure if both bromines add geminal or end up vicinal, and I haven't figured that out yet. So this is as far as I'll ask you guys to go with this particular mechanism. Let's stop again and think about what we've learned so far. So these first 3 reactions were the ones that I kind of paused and looked at a second ago. If we go from the alkyne using specifically hydrobromic acid in the presence of peroxy radical initiators, then in a mechanism that was identical to what we saw with alkenes, we end up putting a bromine at the anti-Markovnikov position. In this particular example, R1 doesn't actually give us a good, because the alkyne that we started with was disubstituted. So there's not really a good anti-Markovnikov in the particular drawing that I have. So I need you to think of R1 in this particular case as a hydrogen, so that you can kind of see how this is intended to be an anti-Markovnikov product. We also looked at earlier how we can start off with a vicinal dihalide, where the 2 halogens are coming off of adjacent positions. Using sodium amide, where the sodium is a spectator ion, we will produce a vinylic halide. And then another equivalent of sodium amide will kind of, without being able to stop this, will rip off the second hydrogen, and that's how we end up with the alkyne. This white arrow right here, instead of being a black arrow, means that there's a problem if R1 is a hydrogen. And hopefully you remember that problem, that if R1 is a hydrogen, then it will actually continue to rip off that hydrogen, and we end up with the alkynide ion. So there's a little bit of kind of color with this particular reaction right here, something that's very interesting about it. Now we looked at the reaction of an alkyne reacting with a halogenic acid. That was the 3rd order reaction. that will ultimately put the halogen and the new hydrogen anti-relative to each other across a double bond. This was similar to what we saw with alkenes, but not identical. With alkenes, it's a second order electrophilic addition. With alkynes, it's that third order electrophilic addition. Once you get to the alkene, though, if you continue to add the halogenic acid, then you'll end up with the geminal dihalide, and this mechanism is identical to what we saw with alkenes. So at this point, hopefully you're comfortable with everything that you're seeing on this alkyne wheel of doom. Ozonolysis of alkynes is different from ozonolysis of alkenes in two ways. First, when you ozonolyze alkynes, you actually end up making carboxylic acids. With alkenes, you ended up making carbonyl groups, specifically aldehydes and ketones. So that's the first major difference associated with alkyne ozonolysis. And the second difference is we do not need to reduce the final products. When we did alkene ozonolysis, we had to add zinc in the second step in order to get the final product. With alkynes, you don't have to worry about that. If you do add zinc, it actually doesn't hurt anything. So you can conduct an ozonolysis simultaneously of alkynes and alkenes and add zinc in the second step that's required for the alkenes, and it doesn't mess up your alkynes. There is kind of an interesting difference between disubstituted alkynes, which is the first example I'm showing you right here, and monosubstituted alkynes. In a monosubstituted or terminal alkyne, the carbon connected to the hydrogen ends up taking on a third oxygen to become carbonic acid. So when we clip this off and then plug those oxygens in, we actually end up plugging in an even additional oxygen. H2CO3 is carbonic acid. It's an inorganic acid. We actually kind of lost an organic carbon, which is a shame, but it's what ozonolysis does in this reaction. The last reaction we're going to look at for alkynes is the alkyne hydration. This is the addition of water to the pi system of an alkyne. Hopefully you noticed on the slide that it's not an alkyne, that's an alkene. And the reason why we're looking at the alkene is to see if we actually have to learn a new mechanism or we can just recycle our previous mechanism. And looking at the alkene mechanism, the pi system swings out to pick up the hydrogen. This is the standard electrophilic addition step, and then we end up with the carbocation. And hopefully already you're seeing the problem that if you try to take the alkene mechanism and just change it out for an alkyne, you have to check to make sure that the alkyne version of that does not produce that vinylic carbocation, because if it does, then the mechanism doesn't work. So we need to come up with something else. And what they found was in order for this reaction to work, they actually have to add in a catalytic amount of mercury 2+. Back in the old days, chemists were bold about throwing mercury in chemical reactions because we didn't fully understand the neurological impacts that mercury was having on people in mercury contamination areas. So this is a very old reaction, and I'm not sure that they do it anymore in the laboratory, but the ACS does not care. You still need to learn it. So in the first step of the mechanism, the mercury metal coordinates with the pi system. This is, as I said before, when we talked about catalytic hydrogenation, we were going to see a coordination step again, and this is that moment. I'm not exactly sure the best way to diagram that mechanistically. The pi system kind of reaches into the mercury, but it doesn't break away from the carbon. This still represents electrophilic addition. The pi system's pushing into that mercury, but the mercury just kind of sags on the pi bond. And what it enables the pi bond to do is in the next step, water will come and attack the more substituted position. This ultimately will produce the Markovnikov product. The water will attack the more substituted position. This pi bond breaks and now becomes a more meaningful association of a covalent bond between the carbon and the mercury. Mercury is a weird metal, and there are all kinds of reasons why it's weird. It's very electronegative for a metal, which makes sense then that it would make some type of covalent bond. And before we move on, we should probably clean up this positive charge, so we're going to use water to deprotonate that. And now you're starting to see the final product take shape, because what we're ultimately trying to produce is something called an enol. which is an alcohol connected to an alkene. The issue, though, is the mercury, which was helpful to us in the first step, now has to be kind of kicked off. And so this, under acidic conditions, so they run this reaction in the presence of sulfuric acid, this enol will unload the electrons from the oxygen, will swing down to form a carbonyl. The pi system reaches out to pick up the hydrogen, and we end up not making a carbocation, but making a positive charge on that oxygen right there. Okay? This oxygen is now positive, so it's pulling electron density back, and that actually causes the whole system to tear those electrons back from the mercury, and we end up with our enol. This is not where the reaction stops. Okay? So this enol is a special name of a molecule where you have both the alkene and the alcohol attached to the same carbon. And these particular compounds are not stable, and they will self-destruct. And they do it through a process called ketone-enol tautomerization, or more commonly just tautomerization. And tautomerization is an equilibrium process where an enol will convert to a ketone. And while equilibrium is true, it does exist in equilibrium, the products are actually favored in this case. The ketone is the most stable form, and that two-step tautomerization tacks on to the end of this mechanism. So it can't stop at the enol. There's no way to stop it. It just keeps rolling right on through. I should have continued the mechanism up here, but I ran out of space, so I just redrew the molecule down here, but you don't have to. You can just keep going right from the end of this first mechanism. The electrons, just like we saw before, where the lone pair on the oxygen swings down, loosens up the pi bond to go out and pick up a hydrogen, and then water plucks off the extra hydrogen, and we end up with this ketone. And so in an alkene, to go back to the alkene, we can convert the pi bond into an alcohol. In an alkyne, when you try to convert that pi bond into an alcohol, you're successful, but you can't stop it there. Without any ability to stop this reaction, it just keeps rolling right on through to the ketone. So an Alkynes hydration reaction will ultimately turn an alkyne into a ketone where the carbonyl group shows up at the Markovnikov position of your alkyne. All right, so now you're ready to consider the full alkyne wheel of doom, or as somebody with a bad sense of humor referred to it, alkynes of doom. The new reactions that I'm adding in here are first looking at ozonolysis, and ozonolysis for alkynes is similar but not identical to ozonolysis for alkenes, and that's because we end up making carboxylic acids. This white arrow right here means that if R1 is not a hydrogen, something weird can happen. And the weirdness is down here in this box. So if R1 right here is a methyl group, then we end up producing these two carboxylic acids. If instead R1 right here is a hydrogen, then go down to the bottom, and there's R1 as a hydrogen. When you do ozonolysis, we end up with a carboxylic acid on one side, but we also end up with that carbonic acid, where we end up with that carbon picking up 3 total oxygens. We also saw the hydration of an alkyne. That's the reaction that involves aqueous mercury sulfate and aqueous sulfuric acid, and that ends up producing the Markovnikov ketone. Also, we looked at what happens if we take the alkene with a halogen and we try deprotonating that with amide. This white arrow tells me that if this R1 group is a hydrogen, then something else is going to happen. And we have to go down to this box right here. Remember that if you made the alkyne using sodium amide, then you will deprotonate that alkyne to make an alkanide ion that can then react with an alkyl bromide to build a carbon-carbon bond. This was one of the first reactions we looked at today, where this has to be a methyl or a primary alkyl halide. It doesn't necessarily need to be a bromide. I should change that for just a generic halogen right there. So this right here is a summary of all of the chemistry that we saw for alkynes. You should be able to show mechanisms for all of these with the exception of the ozonolysis mechanisms.